by the group of Pisa and IAT, and in particular Matteo Bianchi will introduce the group, of course, and we'll talk about wearable haptics, sensing, perceptual and emotional aspects in human-robot applications.
Thank you, Domenico, for inviting me. I'm Matteo Bianchi from Istituto, Italiano, di Tecnologia and University of Pisa. And as a research collaborator of University of Pisa, I'm involved in Wearable project. And in this talk, I will consider some aspects related to wearable haptics. So, the first question is why we need wearability, and why wearability is the new paradigm of haptics. Of course, because it enables to fully capture and reproduce the wide range of human interactions, and also it enables a more natural and effective human-robot interaction and human-human communication. However, wearability is not easy. There is a long road to do because there are some requirements for wearable devices. Of course, we can mention lightweight, but also we need reduced dimensions, which often led to under-actuation and under-sensing approaches. And of course, we need to take into account also perceptual and affective aspects of wearable haptics. So this is our approach to wearable haptics, that we can call from humans to robots and back again. That's to say, starting from humans and from neuroscientific studies, then through mathematical modeling, we can achieve guidelines for system design, for wearable system design that can be used for human-robot interaction, and in particular for sensing, for haptic feedback, and of course we need to take into account the emotional aspects related to human-robot interaction through wearable haptics. So let's start from the first part, from humans to robots. Of course, human behavior is an extraordinary source of inspiration, but merely mimicking this behavior is not easy, is not intelligent. So what we can do is try to achieve a mathematical description of human hand and human haptics, and then using a mathematical language which can be understood by artificial system and can inform an effective device design. So I will show you some examples of this flow from humans to robots with application to wearable haptics, and in particular to tactile displays. So this is a very short summary of this flow. So which lesson we can learn from neuroscience? Then there is a grounded device application, and then we can move towards wearability to increase the range of applications of haptic devices. So this is a paradigm that we had in Pisa, and this idea was developed some years ago by Antonio Bicchi. And the idea is that a large part of cutaneous information used for softness discriminations in humans is related to the force-area relationship. So this is the story of the contact area spread rate. This is the name of this paradigm devices, starting from the early implementation, then moving towards fabric yielding displays, which enables a real-time contact area measurement and a more natural interaction, till the fabric yielding display 2, which is the final grounded implementation of this paradigm, which has 2 degrees of freedom, which can measure force, and which can enable a very accurate cutaneous rendering in terms of contact area control. And this is good, but not wearable. So the final step of wearability is to translate this knowledge on how humans discriminate softness from more refined devices till the final stage of wearability and of a wearable device. Of course, this device then come back to humans because of it can convey haptic stimuli and more specifically soft stimuli. But there is another path again, because if we develop a device, we can investigate whether contact area spread rate, whether cutaneous cues can contribute to proprioception, and then using this idea to inform a new device design. That's to say, in a never-ending information exchange from neuroscientific inspiration and robotics. So the idea that cutaneous cues such as skin stretch contribute to proprioception is well known in haptics, but in our case, what we want to investigate is that does the haptic system use the contact area to estimate the relative displacement of the finger? Because when you push your finger against a compliant object, the area of contact increases, and you can use this information for softness discrimination, but you can also use this information to infer proprioceptive cues. So what we did in this collaboration with the University of Bielefeld is to consider the fabric yielding device too, and to mimic a different stretching state of the fabric, and to mimic a different contact area spread rate while the finger was moved up and down. And then we investigated if human sensory motor system integrated the contact area spread rate information with the proprioceptive cues. This is what we found, that the information for proprioception and touch were integrated to estimate the displacement of the finger, and more specifically, the larger the spread of the area, the larger was the perceived displacement. And this idea is interesting not only under a neuroscientific point of view, because following this finding, we can devise guidelines to reduce the working space of haptic devices which convey proprioceptive cues, because if we control the contact area on the finger pad, we can simulate even different range of motion of the fingers without affecting and without increasing the work space of the device. And here we have, so far we have seen the first path from humans to robot. Now we have the other part that we already started to consider, from robotic devices to human body, to study human body and to understand and to investigate other neuroscientific hypotheses. So these are the three aspects that we consider in this new path, which is sensing, human and robotic sensing, haptic feedback, and affective haptics, to investigate the emotional aspect of the sense of touch, as Domenico and Hong said beforehand. So sensing is important. Developing robotic sensing devices for study human behavior is extremely important, because we need to understand how human control the organ of the sense of touch, which is the human hand. And then if we develop the wearable sensing system, we can enable, as we said, a more natural interaction. So what we have done is to consider both the kinematic and the force sensing for humans, and we developed the wearable systems for these two kinds of sensing approaches. Of course, wearability needs to reduce and to be careful in the number of the sensor that we used, because we need to have limit on the dimension of the sensing system to not interfere with the naturalness of the motion of a human body. So let's start from kinematic sensing. So what we usually have are glove-based hand pose reconstruction system. So they are systems that can be applied in a very wide range of applications, ranging from rehabilitation to virtual reality, etc. However, there is an issue with this system. They can be affected by many non-idealities because, for example, the complexity of the human hand biomechanics and also the measurement inaccuracy. So what a hand pose reconstruction system usually provides is a set of noisy measurements which are limited in number and in accuracy. So these limitations on intrinsic accuracy are strictly related to the issue of wearability. Because of ergonomic issues, we are discouraged to use a very large number of cumbersome sensors, but also for economic considerations. If we consider the CyberGlow, which is one of the most famous hand pose reconstruction system, this system can be endowed with 18 or 22 sensors, but the cost changes dramatically. We have $5,000 of difference. So this is also another reason why we try to limit the number of sensors for this kind of devices. Of course, we can have also more economic devices, but they are not so accurate, so they met scarce acceptance due to their inaccuracy. So our question was how to realize wearable glove for kinematic sensing, but still guarantee a good accuracy. So we can use this model, which is very general, where we have the measurements, the joint of the hand, the noise, and this measurement matrix H. So of course, when we have a reduced number of measurements, we can have an infinite number of solutions because of the null space of matrix H. For example, we can have a simple solution based on pseudo-inverts, but it can be very far from the real hand posture. So how can we improve it? Again, there is the relationship between robotics and neuroscience. We can exploit the idea of hand synergies, that to say that the hands, even if they are different in shapes and dimensions, they share these commonalities, which are covariation patterns in multi-digit movements and contact forces, which are called hand synergies in a broad sense. And this is the most important idea behind the synergies. That's to say, the number of degrees of freedom that can be independently controlled by the nervous system is smaller than the actual mechanical number. Also because of peripheral constraints, but of course also because of central nervous system organization. So this is a very quick animation of synergies, which can be defined as the principal component of a huge database of grasp postures. So this is the first, the second, the third synergies, which take into account the large part of hand pose variability. So what we did is, starting from a kinematic hand model that we can choose without loss of generality, and we collected a data set of grasp postures that we characterize in terms of covariance matrix, which expresses these covariation patterns or synergies, and mean. And we fuse this a priori information using a minimum variance estimation approach with a reduced number of measurements. Of course, these are the first results that we achieved using a very an economic glove based on piezoresistive sensors, which was able to measure only 5 joint angles despite of the 15 degrees of freedom of the kinematic model we use. And we can see that the minimum variance estimation compared to a simple pseudo-inverse method, the blue one is the real posture and the white one is the reconstructed one, provides the best results, even in terms of naturalness of the reconstructed poses. But this is only the first part. We continued to investigate other wearable approaches, even within the Wearable project. So we moved towards another types of sensor, the kneaded piezoresistive fabrics, where we have 2 conductive layers and 1 insulating layers. And in this case, the resistance difference between layers depends on the angles between the tangents on the sensor endings, but it is independent on sensor elongation and bending profile. So they are more accurate than the previous sensor that we use. And this is the tangent angle and the relationship between the difference of the resistance between the 2 layers. And again, we applied our method to only 3 sensors, and we use the reconstruction approaches that we described to classify some poses. And these are the preliminary results in reconstruction that now we are investigating more in depth, and we are validating even in a more quantitative manner. The next step is that, of course, we can improve the existing wearable sensing devices, but if you were the designer, where you can put the sensors and which degrees of freedom you can sense? So the question is how to design an optimal glove when you have a limited budget and some limitations on technology. So again, this nice synergy between neuroscience and robotics. There is a biological inspiration on finding an optimal design. Because if you consider the human hand, you can have different typologies of proprioceptive sensors. So we have a non-uniform map of sensitivities to joint angles. We can have slow adapted units, which are non-localized, and they are rather uniformly distributed, and a fast adapted unit that are denser near joints with a more localized response. So what we can infer from the biological example is that the sensor density needs not to be uniform, and there are better and worse distribution of sensor, probably. And our question is there a preferential distribution and density and typologies of the sensors for designing a sensing glove? So this is the mathematical formulation of the problem, where we try to minimize the Frobenius norm of the square Frobenius norm of the a posteriori covariance matrix, which is still related to the a priori covariance matrix, that's to say the synergistic description of grasp postures and the measurement matrix. And the a posteriori covariance matrix is a measurement of the amount of information that we can achieve about unknown parameters. And this is an interesting result. If we consider different sensing distribution, and this is our cost function, we can see that the first 3 postural synergies can take into account more than 90% of the reduction of the posteriori covariance matrix. And this result is similar to what was observed in the neuroscientific domain, where the 3 postural synergies of human grasp take into account more than 90% of pose variability. So there is this nice dual relationship between controllability and observability. So these are some results. We can see that with the optimal glove design, we achieved better result compared to the non-optimal design, even if in this case the results are good because we use the a priori information to complete the reconstruction starting from only 5 sensors. And then we can move towards force sensing. So why it is important to measure force? To understand the human grasp, because we ideally need measurement on individual digit, posture, contact point, contact forces, and torques. So there are different approaches in literature: sensorized objects, which can provide reliable measurements, but they have no versatility, or sensorized hand that can be worn by users. And then we have a Timbot sense, which is a ergonomic wearable. And this is, it consists of this shell where we put a force torque sensors. And this is where Timbot sense can be placed within the general framework of force sensor systems. So it is able to provide normal shear forces and torques. It is able to provide the contact point information. It is able to allow an unconstrained grasp to the user because it is wearable. We have this point, the cutaneous cues, which is not natural because we have this shell on the finger pad, but we are investigating also this aspect because it can be a useful tool even in this case. So this is the idea of the Timbot sense. So knowing the force torque measurement and the geometry of the surface, we can compute the contact point based on the intrinsic tactile sensing, and we can achieve a very nice force measurement accuracy with error less of 0.1 Newton and contact point estimation in the order of millimeters. So this is a wearable approach, and then these are some functional tests using the Timbot sense. And, of course, the video doesn't work. Okay, should work now. No. It's not wearable, the video. And these are another nice application of the Timbot sense with the robotic hands, because it's a kind of closing the loop between humans and robots, because this shell can be worn even on commercial rigid hand and also on under-actuated soft hand like the Pisa IAT soft hand. So finally, the last aspect of wearability is the affective aspect, because touch, of course, as Hong and Domenico said, is a very important sense also in evoking human emotions. And is interesting because in this study of 2006, it was demonstrated that there are universal emotions that can be communicated purely through touches. And also touch intensifies the emotional displays from other modalities. So these are some background, because there are a long tradition of studies on affective touch. The first one is in 1895, and then there is a long path toward affective haptics. And wearability and affective touch is another synergy that this part and this paradigm poses, because we can have non-wearable and a wearable device. But when we have wearable devices, we have no bulky barriers for affective touch. We have flexibility and customizability when we have to apply some devices to patients, and we have cutaneous informations. And then we can use affective haptics to assess the acceptability and effectiveness in stimulus delivery of wearable devices, and even to inform device design guidelines. Of course, what we did with other colleagues in Pisa is that we tried to model emotions using the Russell circumplex model of affect, where we have two dimensions: the arousal, how strongly the emotional stimulus is felt, and the valence, how much an emotion is perceived, using the SAM, the self-assessment mankind, to categorize these levels. And of course, the autonomous nervous systems is also related to the emotion part. So we can exploit some physiological parameters, some physiological response to assess the emotional response to haptic devices. So this is the device that it was previously shown even in the talk of Domenico and Hong, which simulate the caress by controlling the velocity and the strength of the caress. And what we did is to perform a preliminary characterization considering the SAM and also the electrodermal response, which is the impedance, the dermal impedance, and is directly related to the sympathetic nervous system, and the dynamic is strongly affected by the emotional changes. So what we found by considering 5 levels of force and 3 levels of velocity is a positive correlation between the arousal scores and the strength of the caress. That's to say, an increasing arousing tactile stimulus can be observed when we increase the force of the caress. A correlation between the valence and the force in terms of the pleasantness, which is inversely related to the strength. And this result, which is also confirmed by previous studies, a negative correlation between valence score and the velocity. The slower the caress, the more pleasant it is felt. And these are also the result in terms of the post-hoc differences between the valence and levels of velocity and forces. And also what we found, and this is an interesting result, considering the electrodermal response, we found that in terms of valence, we are able to statistically discriminate, considering the maximum value of the phasic components of EDR, to statistically discriminate the 2 categories of pleasant and unpleasant stimuli. Despite of this result, this is very interesting because it shows that the mechanical skin stimulation produced by this device seems to be able to elicit an autonomous nervous system change. So what we are going to do is to better investigate using different types of signal and also physiological response, and to start also a protocol to understand the difference between the artificial and the human caress. And it is nice because from the very preliminary test, the participant did not recognize the difference. So this is what we found. So closing the loop, so the affective assessment can be used also to understand and to increase user acceptability when we consider wearable haptic devices, for example, for long-term applications such as prosthetics. And this is another topic that we are developing as University of Pisa and IIT, because one of the challenging topic in prosthetics is to close the action perception loop, because despite the development in terms of prosthesis design, we need to provide also the sense of touch to these devices. And so the feedback can help in establishing also a sense of embodiment and ownership of the prosthesis. So we can provide feedback in terms of the grasp force and also high frequency feedback in terms of contact acquisition. In this case, wearability is the conditio sine qua non, that's to say is mandatory in this application. So if we apply wearability and also affective haptic characterization, we can also inform a better design of the wearable haptic system for prosthetic applications. So this is very quickly what we did. So by using the Pisa IT soft hand, which is a soft under-actuated hand, we use an interaction torque observer to convey force information. This is the first adjustable press cuff that provides the grasping force of the prosthetic hand based on this interaction torque observer. And then we also provide high frequency feedback because touch is also a dynamic sense. So high frequency can be used to detect texture, contact, and slippage. And this is very similar to the old hi-fi, where we have a needle, an accelerometer, an amplifier, which is an hi-fi amplifier to minimize distortion, and then a loudspeaker, that's to say an actuator that convey back the high-frequency information to the user. So this is what we did. We use some accelerometer, and we use some vibrotactile motor, and we convey back the sense information from the tip of the soft hand, which is the hand we developed in Pisa and Genova, to the actuators. And what we found is that the wearable force and the texture feedback increases the user performance in healthy subject, in object discrimination and grasp stability. So in conclusion, what we can say is that wearable haptics can represent the key to advance the state-of-the-art in human-robot interaction and human-human communication for a more natural and effective interaction. But only for our belief is that only following this multidisciplinary approach, combining neuroscience, affective computing, robotics, and control engineering, we can fully take advantage from wearable haptics paradigm. This is the final scheme. Thank you very much. This is a nice wearable haptics applications.
On the air skin.
On the hair skin, yes, because of the emotional aspect. Domenico followed the topic very well.